So in this demo, we will see how our hardware can be used for classifying one-dimensional waveforms. We will be using a particular application called spike classification. The purpose of spike classification is given any spike waveforms, we need to label it whether it's belong to class 1, 2 or 3. If the spikes were ideal, it was much easier to just do the template matching, but in actual cases the waveforms are very noisy and it becomes difficult to classify. Say if the waveforms are very noisy like this, it is very difficult to label this as to be 1 or 3. So this is the GUI for the spike classification using our hardware. So we have 4 databases, each consisting of 3 classes and different noise level from low noise to high noise, and each of these sample consists of 64 time samples of data which are sent from PC to an FPGA via a USB link. This FPGA forwards the same raw data to our machine learning hardware, which does the ELM first stage. The output of IC is given back to FPGA, which needs to do only few additions to get the result, and the classification result from FPGA is sent back to PC. And as you can see, this is the classified label whether this waveform belongs to 1, 2 or 3. So now maybe we can classify this using our hardware. As you can see, with this input waveform, the system was correctly giving the label as this waveform is class 3. In this demo, we can also explore the accuracy versus resource trade-off. Say we select a low noise version. In that case, we don't need all the 128 neurons on our chip. Maybe we can just select 32 hidden neurons out of those to save power. So let's check what is the accuracy with such lower resource usage. So we want to classify 30 spikes in a batch mode. As we can see, even with lower energy resources, it is able to classify 27 out of 30 spike waveforms correctly. What happens if we increase the noise? Say we choose the maximum noise source. As expected, the classification results became poor. So one way to regain the accuracy is to increase the hardware usage. Say we decide to use 96 hidden neurons and we classify the same 30 spikes again. As we can see, if the input source is more noisy and more difficult to classify, we can always use more neurons on our hardware to get better accuracy.